Okay, so let's continue on with some meandering rivers. So we talked about how streams can move material. So now we just want to look at some of the features, and one of those that we see a lot is what's called meandering or meanders. And so rivers that have low gradients do not flow straight, they actually curve. And over time, the shapes of the rivers are being changed by the velocity of the stream. So what we see here in a very low velocity, low gradient area is a stream that's moving around. It's meandering, if you will. And what we see is that there's two kind of features forming here. On the outside bend of a river, so let's say the water's coming from the top of this diagram, moving around here. As it comes out here, the highest velocity in the stream is pushed to the outside here. And what that does is it starts to erode into this material and form what's called a cut bank. And the material that comes, or the water that comes around the inside here, is the slowest velocity. And so it actually dumps some of that stuff that it's carrying, some of that stuff in suspended load and bed load gets deposited here. And so over time, this bend will actually grow this way towards this cliff here. And this deposit will follow it. And so this shape will change over time. And so we can get what's called an oxbow lake when we actually have really tight meanders like this. They can cut off this space here and abandon this loop. And the new path of the stream would be here. We have this kind of leftover. That's what this is representing, an old path of the stream. So just a few other images, right? Cut bank, point bar, cut bank, point bar, cut bank, that kind of thing. Some real images, right? So some smaller streams still have those features. Outside bend is the cut bank, inside bend is the point bar. More images. All right. And then hopefully this little animation that I have for you right here will be helpful. So let's reset this. So here, let's say, is our stream. Low gradient. It does have some meandering going on. There's some material here that's fairly resistant to weathering and erosion. But over time, what we see is the movement of my stream around as it moves around is actually cutting laterally or horizontally, widening my valley here, creating the floodplain. So that when we come along and we see our stream today, it has this kind of meander look to it. And it also can have these little oxbow lakes left behind, which tell us where the stream used to be. So how do we get an oxbow? It looks something like this, where the stream is moving around. Remember, outside bend erosion, inside deposition. And so this is an outside bend. It's cutting this way. That's an outside bend. They're pushing toward each other. So eventually they can meet and cut off this part of the stream. And now the path of my stream is different. And I'm left behind with this little oxbow lake thing, right? So that's how those things form. And then we can use those to figure out how the stream has gone over time. But you could see this is a fairly large floodplain. We don't get this when we look at very young streams. Right? They don't have this floodplain because they're not meandering side to side. They're carving downward, right? Want to remember that kind of good stuff there. All right, so what do we got next for you? So the development of the floodplain. Remember, it is this flatter area adjacent to these low gradient streams that are meandering. It's mostly composed of material that has been deposited by floods. So we know that the stream contains material, right? Suspended load, bed load, that can be brought out and deposited here, and we kind of fill this in, right? And this is why people live here and farm here, because it's usually good material, good soils to grow things in. Okay, let's see. Is this where we want to be? So what we want to look at next then is talking about the different types of floods that occur. And so there's a couple things that we can do to evaluate flooding, right? So some terminology that we might use when we talk about floods, we might look at the hydrograph. What is that? All that is the graphs to the right are examples of that. They're a plot of the discharge. Now remember, discharge is the amount of water that moves past a certain point, right? So, and it's a volume, right? So we use cubic feet per second. So what you're seeing on the right is that there is a stream that has a normal discharge when there's not in flood stage. But then when there's an event that causes lots of water to move into the system, the amount of water moving in the system increases. So I start to get this rise in discharge, right? More volume is moving past until I get to this peak area where there's the biggest part of the flood, and then of course it will recede after time. Now, there's a couple things we can look at here. There's the lag time, because there's an event, let's say heavy rainfall. Well, every drop of water doesn't instantly go into my stream. It has to hit the ground and then move toward my stream to get in there. And so there's a little lag there between the event and the flood. And certain rivers have a larger lag time than others, and certain types of floods do, right? So the flood stage would be above that stage where it's probably overtopping the channel and affecting society, right? Buildings and people and things like that. Now, we can use some data to determine how often these floods show up, right? So we're going to call that the recurrence interval. It's just an average like we do for lots of things. We can't say absolutely, every 5 years there will be this size flood, but we can tell you on average how long that would occur. In order to do that, we need some data. And so if we collect some discharge data, right, how big have the floods been over the past, let's say, 50 years? If I'm monitoring my river, I can evaluate that and say, yes, last year we had a discharge that was 10,000 cubic feet per second. And that was big enough to overtop my stream and flood the town. Next year, there was a 5,000 cubic feet discharge, was the biggest one that year. That was fine. The river was able to handle that and it did not flood the town. And we could keep taking data like that over time. And if we see that every 5 or 6 years, a 10,000 CFS cubic feet per second flood comes along and impacts my town, then I can do the math and say, okay, every 5 years we need to be prepared for that size flood. And so in general, we could do something like that. And so the recurrence interval is something we would say is in years, right? So what's the recurrence interval of that flood? Oh, it's every 10 years, or it's every 25 years. We can also do probabilities. What's the probability of that size, that 10,000 CFS flood? What's the probability of it happening this year? Oh, it's 1 in 25. So it means there's a 4% chance of it happening this year. So we can do both these things, the recurrence interval and the probabilities. Now in lab, when you do the lab portion of this, you're going to be able to calculate these. I'll show you the calculations here really fast. They're not that complicated, of course. Let me not skip over them. Recurrence interval, what we need is the number of years that you've kept records on that stream. So that's important. Have you kept it for 5 years, 100 years? Right? 10 years, we need that number. And then what we do is we look at all that data. So let's say it's 50 years. We'll look at 50 years of data. And every year we'll see what was the biggest discharge on that river system. So in order to figure out how often a specific flood occurs, we would then rank every one of those from 1 to 50. The biggest one, the one that had the most discharge, we'd rank number 1. The one that has the second biggest, number 2. And we'd rank them all the way from 1 to 50. And so if I was curious about the third biggest flood that ever happened on my river, the one that I ranked 3, that would be the number that I would put for M. And so I would have 50 plus 1, so 51 divided by 3, and that would tell me how often in years that size flood would occur, the number 3 size, whatever that value was. And then, of course, if I wanted to see, what about the biggest flood ever? Well, I'd put the 1 for M, and then the top number would stay the same. Or what if I cared about the 23rd ranked flood that occurred? Well, I'd put 23 for M. And each of those answers would be in years. And usually what you'd see is the really big floods, they're rarer, right? So the 1s and 2s, the ones that you rank the highest, those don't occur as often. But the smaller floods, they do occur more often. So that's the recurrence interval. If we wanted to know the probability, we would just take that answer, which is t, and we would place it in the probability equation there. So 1 divided by t times 100 would give us a percentage, right? What's the percent chance that that size flood that we just evaluated for the occurrence interval would happen this year? Is it a 2% chance or a 20% chance? So look, this is kind of important in that this is how we evaluate flood hazards, right? We take this data and we say, hey, you're living in an area where there's a flood every 5 years that hits your house. So maybe I don't let you build there. Or maybe I say, you need flood insurance. Or maybe I say, you need a lot of flood insurance and it's going to cost you a lot of money to live there. Or your chances of being impacted are super low, 1% chance. You don't need flood insurance. So this little bit of data here, this pretty simple equations that we're using, are used by insurance companies to determine who needs flood insurance and who doesn't. Okay, so that's some terminology. Yes, we're taking a break, and let me, and then we'll talk about the two main different types of floods that we want to discuss.